Hi again, and welcome to the 6th video, well 6th or 7th depending on how you're looking at this, lesson on integration for Year 13 in Edexcel's A-level course. So I've done another video on how to integrate by parts, which is the focus of this lesson, integration by parts. This video is going to show you just the traditional approach for how to do this, the same way that I was taught myself. I'll link you in the description to another method, which I'm calling the DI method, but I won't go into this here. And so this video is the traditional flavour of how to integrate using the method called integration by parts. So we'll have a look how to do this with the help of several worked examples this time. But before we do that, I'm going to show you some warm-up questions to attempt. And obviously, as you know, try them first. There's two, in fact, to have a go at. The first one is about a binomial distribution, and the second one is solving a trig equation. So press pause now and press play when you're ready to see the solutions. So assuming you've done that, let's have a look together at the solution to warm up question 1. Question 1 is about a nursery which has a sack containing a large number of coloured beads, of which we're told 14% are red. Alia takes a random sample of 18 beads from the sack to make a bracelet. Part A, we need to state a suitable binomial distribution, so we're told it's going to be binomial, to model the number of red beads in Alia's bracelet. So we can let X be the distribution, and what I'd suggest we do first of all is let's just call X B for binomial. The first parameter is a number of trials, so if she's taking 18 beads, that's going to be 18 beads. The second parameter is P for probability of the event happening. So 14% are colored red, there's going to be a 0.14 chance of picking a red bead. Part B, we're now going to use this model to calculate probabilities. So B part 1, we're going to calculate, using this model, the probability that Alia has just picked one red bead in her bracelet. So what we're going to do, we're going to get the calculator up and ready. Different calculators will do this in different ways. The Casio ClassWiz, this version is my personal favourite. So we're going to go to menu, distribution, going to go to binomial, and this time because we're trying to find an exact probability, just one bead, I'm going to click binomial PD, which is number 4, and then I'm going to go to number 2 for variable. So I want to work out the probability of picking 1 out of 18, so big N is 18, where the probability of picking a single red bead is 0.14. Press equals and equals again. That generates a probability of 0.194. So that's our answer for question B part 1. So part 1, probability of X taking the value of 1 is 0.194. Part B, part 2 is slightly different. It says what's the probability that there's at least 4 red beads in Alia's bracelet. This one here is different because we need to work out now the probability of X being at least 4, so we need to use an inequality. The calculator generates probabilities leading up to and including a certain value. It doesn't work out a value or greater. So what we need to do is to think of this in a different way. The chance of the number of red beads being 4 or more, that's going to be every single possibility you can imagine. That's a 100% chance, apart from, of course, the probability that she picked 3 or less. So we need to do this step here to work out the chance of what 4 or more would be. So 1 minus the probability of X being less than 3. This time, because it's an inequality, a range of values we're interested in, 0, 1, 2, or 3. We can go back to the calculator, but this time we can change from it being binomial PD to binomial CD, which is the cumulative binomial distribution, because after a range of values all the way up to and including 4, rather up to including 3 is what we're working out. So press 2 for variable. So what's the chance of getting 3 out of 18 or fewer if the p-value of just getting one of them is 0.14? Press equals. We'll get 0.7618 blah blah blah. So 0.7618, etc., etc. So we need to do that calculation now. 1 minus this. So go back to menu, normal mode. 1, take away the answer I just got, gives 0.238. So that's B part 2. Part C, we have to comment on the suitability of a binomial distribution to model this situation. Well, one of the things we need to hold for a binomial model to be appropriate is that the probability of picking a red bead, or generally speaking the probability of an event happening, needs to be fixed for each trial. So here, each time we pick a red bead, that will actually lower this percentage. So it's not going to be a perfect fit for the binomial. However, it could be a pretty decent fit if you're talking like thousands upon thousands of beads, for example. If 18 beads are taken out to make a bracelet, then the more beads you have, the more it's going to be like a drop in the ocean in terms of affecting the overall picture. So the more beads, the better. It won't affect this 14% too much. But for example, if you're only, say, 40 or 50 beads in the bag, picking 18 out would be hugely significant. So it's a bit awkward to word. This is the best I could come up with. I'm not saying this is perfect by any means. So I'd say something like a binomial model could be suitable if the number of beads is very large, such that removing 18 beads has a negligible effect on the proportion of red beads still inside the bag. Something along those lines should pick up the mark for you. Moving on towards part D now. After several children have used the beads from the sack, the nursery teacher decides to test whether or not the proportion of red beads in the sack has changed. She takes a random sample of 75 beads and finds 4 red beads. So, stating your hypotheses clearly, use a 5% significance level to carry out a suitable test for the teacher. So, it's going to be hypotheses, that's plural of hypothesis. So we're going to have H0 and H1. In fact, I'll put H1 on the top line as well. Never mind, I won't. So H0 is assuming that nothing has changed. This is called the null hypothesis. And so if nothing's changed, I often think of the null hypothesis as well as being innocent till proven guilty, if you like. Assuming nothing's changed, assuming what you've told has been true, unless there's evidence to the contrary. So what we're told here is that 14% of the beads are red. So H0 is, that's going to still be the case. So we can assume the probability of a red bead is going to be 0.14. But what's happening here is, we want to see whether or not the proportion of red beads in the sack has changed. It doesn't say if it's changed on the large side or gone lower. It just means, is it different? So this is actually, without quite saying it, a two-tailed test. So our alternative hypothesis, H1, is now P is simply not a 0.14. And so we can imagine this as a binomial distribution now. So if I just sketch on a bell curve like so, where obviously at the top is going to be 75 beads, down at the bottom end is going to be 0. And it says here that from 75 beads, she's found only 4. What I'd always tend to do is think about what the mean would be, or the most commonly expected value. If there were 14% coloured red and 75 are picked, we'd expect the peak to be at 14% of 75. That would be what you'd expect to happen. So what would that be? So 14% of 75 comes out as 10.5. So you'd expect 10.5 red beads, typically. Here though, only 4 have been actually selected or picked out. So what's actually happened is only 4 have been picked. I always tend to do this so you can imagine and see quite clearly which tail you're looking at. We're looking here at the lower tail. So what was the chance of that actually happening? What's the chance of getting 4 or less? So probability, assuming H0 to be true, of X taking on a observed value of 4 or less, we can now calculate. So menu 7 CD, because we want in a range, a cumulative probability from 0, 1, 2, 3, or 4. What's the chance of getting 4 out of 18 if the probability of picking a red was indeed 0.14? So Daisy, what have I done here? So 4, not out of 18, my bad, it's 75 in this question. I thought it seemed a bit strange. 4 out of 75, apologies. That gives a value of 0.0151 approximately. So this here represents a probability of 0.051. We can now compare this to the level of significance for our test. So that's 0.0151. But we wanted to test it at a 5% level of significance. 5% significance level, if it's a two-tailed test, means that we consider this significance split into 2 evenly across both tails. So 0.0151, that's about 1.5%. So that's a tinier bit of a tail than what 2.5% would be, because 2.5 is half of 5. 2.5% would be a bit more than 1.5%, so would therefore be covering more of this tail. So 2.5% in the higher tail would be something like this. 2.5% in the lower tail would be like this. So we can see that the observed value of 4 is within the critical region. So we can conclude here by saying, because 151 is less than 0.025, the value is significant. So therefore, we're going to reject H0, and we can conclude the proportion of red balls has changed. Not balls, sorry, beads, it's saying. So reject H0, proportion of red beads has changed. We can now start to consider part E. So part E, we need to find the p-value in this case. The p-value, in plain English, just means the probability of an observed value taking that actual value. So what was the chance of getting 4 or less? It was 0.051. Anything we need to do now, if it's a two-tailed test, we use a symmetry and multiply that by 2. So the proportion here in both tails for symmetry would be 0.0151 multiplied by 2. So 0.01506 or whatever it is to be more accurate. 0.0150 multiplied by 2. So that's the answer. Go back to normal calculator mode. So my answer multiplied by 2 is 0.0301. So I'm going to write this down, and that's essentially my answer. So 0.0301. This is another way to illustrate that our test was significant, because this represents 3%, which is lower than the level of significance. So therefore, considering this option here, that's therefore significant as a result, because 3% is less than 5%. Let's have a look at warm-up question 2. Question 2, we need to solve theta for the interval from minus 180 degrees up to positive 180, the equation 9 sine 2 theta equals 16 tan theta, giving answers where necessary to 1 decimal place. So first off, we need to spot here that we're not talking in terms of the same stuff. We've got a 2 theta here and a theta there. So what we could probably do with doing is changing sine 2 theta in terms of sines and cosines using the double angle formula. So if I just rewrite this now as 9 lots of 2 sine theta cos theta, just switching sine 2 theta for its identity here, that gives 16 tan theta. And here for tan theta, I'm going to rewrite it in terms of sine and cosine. So that's 16 times sine theta over cos theta. So it might be tempting to think I've got sine on both sides, let's divide through by sine theta. When it comes to A level, and especially trig, try to solve by factorising rather than dividing through. If you divide through by sine theta, two things might happen. You might lose a solution, and also, for all you know, you could be dividing by a 0, which is a big no-no. If sine theta were equal to 0, for example, if theta were 0, and look here, 0 is in this range, so definitely don't be dividing by variables, instead try to factorise. So you can't divide by variables, but there's nothing to say you can't multiply by them. So to undo this being over cos, my suggestion next is to multiply both sides of this by cosine theta. So on this side, I'm going to have 9 times 2, which of course is 18, sine theta, cosine times cosine gives cosine squared, and over here, I'll just have 16 sine theta. Now, I'd get it all to the left-hand side by subtracting 16 sine theta from both sides. That then gives me 18 sine theta cos squared theta minus 16 sine theta equals 0. We can now factorise, and also we could divide through by 2, because 18 and 16 are both even numbers. So we can factorise out sine theta, and because that's going to go to 9 and that's going to go to 8, I can then include this in the working. So I'm going to have sine theta, brackets, then that's going to give me 9 cos squared theta on the inside, and then I'm going to go for minus 8 here, because obviously I've divided through by 2, I'm going to have minus 8 equals 0. So because we're going to be solving a trig equation, and my preferred way is a cast diagram, I've just got one ready here. So one thing we can now do, if I just section this out because I'm running out of space ever so slightly, you need to consider how this can be solved. That is not a straight line. That's a bit better. So it's either sine theta is equal to 0, or this here is equal to 0. So sine theta could equal 0, or it could be the case that 9 cos squared theta minus 8 equals 0. This one's easier to solve. If sine theta is equal to 0, you could actually do this using your calculator, to be fair, or just know it, to be honest. You should know that sine 0 is 0, and using the properties of a sine graph, sine 180 is 0, and indeed sine minus 180 is 0. You could use a cast diagram if you really wanted to. The principal value would be 0 degrees, so using the cast diagram, that would just be these axes. So the axis is going to be on the 0 lines, and to get to 0, it should be 0, or turn around and do 180. So from this one here, we've got solutions which are going to be the following. So if sine theta is equal to 0, in this range, from minus 180 up to 180, we can say therefore theta is going to be minus 180 degrees, could be 0, or could be positive 180 degrees. On the upper end, not on the upper end, sorry, this one here, 9 cos squared theta minus 8 equals 0, needs rearranging. And so if I add 8 to both sides and then divide by 9, I see that cos squared theta needs to equal 8/9. Square root both sides and consider plus and minus. Cos theta needs to be plus or minus the square root of 8, which is 2 root 2, over the square root of 9, which is 3. Again, not enough space. I seem to be very good at doing this. I'll never learn my lesson. So we can take the principal values for this. So we can do cosine minus 1, 2 root 2 over 3, which gives 19.47. The minus option is 160.53. Obviously it says to give it to 1 decimal place though. So from here, I can say that theta is either going to be, it was 19.5 to 1 decimal place. I'll do the other one in a moment. So 19.5, if we just use a cast diagram, then what I can say here is 19.5 will be there. So call that 19.5 each way round. So theta could be 19.5, and here, considering the positive 2√2, if theta is positive, I could also be looking in this bottom quadrant as well. So I can have theta being 19.5, this one, or because we can have positive 2√2/3, we can also have cosine being a positive thing down here, and we can have negatives in our range. So we could go to minus 19.5 as well. So from this one, theta is 19.5 degrees, or minus 19.5. And from the minus option, minus 2√2/3. Again, just checking the calculator to show you, we had 160.5. If you notice here, 160.5 plus 19.5 adds together. So actually, weirdly, this is still the same angle. So if theta is negative, then theta could also be along here. So it could be in the S quadrant, or it could be in the T quadrant. So that way round is 160.5. I can't go to T going this way round, because that would be more than 180 degrees, which is outside of a range. So to get to this one, you have to go that way, which would be minus 160.5. So the two options where theta is plus 2√2/3 are those two, and where theta is negative 2√2/3, I've got 160.5 and minus 160.5. So putting them all together, all the solutions, I've got these 3 for sine theta being equal to 0, and these 4 from cosine theta. So for part A, the full solution is as follows. So A, we've got theta equals, could be as low as minus 180, could be minus 160.5. In fact, I'll get the red line ready so I can underline my answer. So it could have minus 160.5 degrees. Could be minus 19.5 as well. Could be 0. Could be positive 19.5. Could be positive 160.5. And finally, because we're up to 180 inclusive, it could also be 180 degrees too. So that's a full range of what theta could be. That's a full solution set. Part B, it says to deduce the smallest positive solution to the equation 9 sine 2x minus 60 equals 16 tan x minus 30. So the best way of considering this, I think, is to consider it as a graphical transformation. So essentially, this here, if you consider this to be f of x and g of x, in terms of graph transformations, from this here, it's like, call it theta rather, because it's in terms of theta, not x. This here, 2x minus 60, and especially here it's easy to see, this is a function of g, theta minus 30, or x minus 30 now it's saying. So what's happening is every entrance of theta has been replaced by x minus 30. If you remember graphical transformations from A-level and even GCSE, inside, opposite. In other words, it looks like we're going to subtract 30 from each of these solutions, whereas actually we add 30 to the solutions. So make the solutions for theta 30 bigger. The smallest one which will pop out to be positive will be this minus 19.51. And so we take minus 19.5 and then add 30 to it, and we get 10.5 degrees to 1 decimal place. Now that we've tried these warm-up questions, let's make a start on the main body of the lesson, which is integration by parts. Integration by parts then. What is it? Why does it have this name? Well, in chapter 9, which was differentiation, if you recall, we saw that an algebraic product can be differentiated using what was the product rule. So to summarise and take you back to that, the product rule says that if you're trying to differentiate a product with respect to x, where the product is some function u of x multiplied by some function v of x, then we can simply take the product of u multiplied by the derivative of v, then add to that the derivative of the function u multiplied by the function v. We can now make uv prime, or uv dashed as I sometimes call it, the subject of this by subtracting u dashed v from both sides and then putting uv dashed first. So we can see that uv dashed is the derivative of uv minus u dashed v. What we could do now is integrate both sides of this equation with respect to x, and this result leads to what is known as integration by parts. So it's by parts because there's two different parts to it, and if we just integrate both sides, we'll get this result. So uv dashed becomes integral of uv dashed dx. The derivative of uv, if we integrate it, we'll just get uv back itself, because integration undoes the differentiation here. So we just get the product of u and v. And then minus u dashed v becomes the integral minus the integral of u dashed v with respect to x. So this is a crucial result, one of the biggest in the entire course, in fact. We use integration by parts when we have a product of two functions that cannot otherwise be simplified or manipulated into a function we are able to integrate using any other method we know. So if we need to integrate a product of two functions when there's no obvious simplification to see and a u substitution doesn't seem to work, then in almost every other case, this result here, integration by parts, is the technique we need to be using. So, what to set as u and what to set as v dashed? So as we can see, to use the integration by parts method, we need to be able to differentiate one of the functions and to integrate the other. So u is a function we need to first differentiate to get the u dashed from the u. So we can simplify this question by just considering only the function u. So in other words, if we can just figure out what to assign as u, we therefore integrate the other function, and the other one must therefore be v dashed. So just let's focus on what to set as u. Luckily, there is a decent mnemonic for this. So that's layat, and because we don't use inverse trig functions, which is I, you could get away with just saying late. So remember late or layat to be full. So what on earth is layat? L stands for logarithms. So this is what you'd prioritize u first and foremost. So if you see any logs, if one of the products is a logarithm, in other words something like ln kx, that's what you set as u. Next on the list of priority is inverse trigonometric functions like arcsine kx, arccos kx, arctan kx. As I've said, you don't normally need to consider I, but I'm going to put it in for reference because it might be that you're a further mathematician or just interested, so I've included I anyway. After I, the A just stands for an algebraic expression, for example, x squared plus 1, x to the minus 3, or some polynomial function. T stands for a trigonometric function, so sine kx, cos kx, tan kx, and other standard results, and by standard I mean the things found in the formula book, which you would be expected to know. And last but not least, the last thing ever you'd want to set as u is an exponential, e to the power some constant multiplied by x. So just to explain again, we assign u as a first type of function found on the above list, then therefore the other function we therefore assign as v dashed. And also, like I said earlier, you don't need to integrate inverse trigonometric functions on this course, so I've just included I, the full acronym LIAT, for reference only. So let's see how the actual process works when we apply it to some integrals. So, worked example 1, we're going to have a look at how to integrate ln x dx. This is an absolute must-know. You're probably thinking, how is this at all even an integration by parts question, as it's not even a product? We simply just have ln x on its own. Well, this is still a product. What we need to do is to rewrite this as ln x multiplied by 1. And so I'd suggest that's going to be our first move. So let's call the integral same as ln x multiplied by 1. We can now think about what to assign as u and v, then we can use this here, the integration by parts result. So using the LIAT acronym, our u is going to be ln x, because ln x comes before any constant. So the constant, even though it's not algebraic, think of this as being x to the power 0 if you really like. But because log, LIAT, L for logs comes first, and we have a natural log here, we just set that as our u. Therefore, v dashed is forced to be 1. So now, if we were to differentiate u dashed, if we differentiate the ln function, we just get 1 over x. And if we integrate just the constant 1, that of course will give us x back. So after assigning u and v dashed, therefore getting u dashed and v from that, we can now use this general integration by parts result. So I'm just going to box off what we have here because I don't want this getting in the way. We're going to use it, but this is like a little aside to help us to actually integrate this. So it's going to be u multiplied by v dashed, which is going to be, sorry, u multiplied by v, I mean to say. So u times v is going to be x times ln x. I'm going to write x first because I think ln x times by x could get confused with ln of x squared. So I'm going to subtract away the integral of u dashed, which is 1 over x, multiplied by v. Now u dashed multiplied by v is 1 over x multiplied by x, which just actually becomes 1, because 1 divided by x times by x will cancel essentially. So we're going to have x ln x minus the integral of 1. 1 would just integrate to just a single x, then remembering the constant of integration plus c, and we're done. So that's a very easy integration by parts example, but the clue here is to integrate ln x, we need to do ln x, then multiplied by 1. So to consider it as a product of a natural log and just the unit constant 1. Work example 2, x cosine x dx to integrate. So again, if we think of the LIAT acronym, A for algebra comes before T for trigonometric, and we have something algebraic and something trigonometric, so therefore x takes precedent for our u. So we're going to say u is going to be our x, therefore u dashed, differentiating x just gives us 1. If our u is x, that forces us to have v dashed as cos x, therefore if we integrate cos actually integrates to positive sin x. So we can now use the integration by parts result, which is here, and apply it to the integral we want to work out. So u multiplied by v will be x multiplied by sin x. So I'm going to call that x sin x. Then we're going to subtract away, we're going to subtract the integral of u dashed multiplied by v. Well, u dashed multiplied by v is just 1 multiplied by sin x, so that's just going to be the integral of sin x with respect to x. We need to recall that sine differentiates to positive cos, but it actually integrates to negative cosine x. We need to remember the constant of integration, and so what this will give us when we simplify these double negatives, we're going to have x multiplied by sin x plus cosine x plus c. Worked example 3. We need to find the integral now of x squared multiplied by the natural log of x with respect to x. The acronym LATE or LIAT again. We have something algebraic, and L for logarithmic, however, comes before A for algebraic. So although the A here is written first, the algebraic x squared, because you have a logarithmic function here, logarithmic, I mean to say, can barely say it, we need to put ln x as our u, because L for logarithms takes precedent. So u we reserve as ln x, therefore our v dashed is forced to be x squared. If u is ln x, then u dashed, differentiating ln x, gives us 1 over x, and if v dashed is x squared, then v, the integral of x squared, becomes 1/3 x cubed. So we now have our initial setup to evaluate this integral. So just remembering the integration by parts result, if you need, I'll put it up again. Here it is. The integral of this, now we've assigned u as ln x and v dashed as x squared. We're going to take the product of u and v, which is going to be 1/3 x cubed multiplied by ln x. So we can write this down first. Now we're going to subtract away the integral of u dashed multiplied by v. So 1 over x multiplied by x cubed, that would give us x squared, but we'll multiply by this 1/3 as well. So we're going to be integrating 1/3 x squared with respect to x, all subtracted away. So then we're going to have 1/3 x cubed ln x. X squared will integrate to 1/3 x cubed again, but we've got 1/3 of that, so it's going to be 1/3 of 1/3 x cubed, but because this is a minus, we put minus 1/9. Then we're going to go x cubed, and of course plus c at the end. Don't forget the constant of integration when we're doing indefinite integrals with no limits attached. Worked example 4, find the integral of x squared e to the 3x dx this time. So for this one, what we need to consider is the possibility that we may need to use the integration by parts technique more than once. We'll see why in a second. Using the LATE acronym, we have something algebraic, x squared, and something exponential, e. So we have an a and an e. LATE, the a comes before the e, or LIAT if you want to include the I, but either anyway you want to look at it, the x squared is going to take precedent because a comes before e on the LATE acronym. In other words, to put it very simply, we just set u as x squared. Therefore the v dashed we're going to assign as e to the 3x. If I differentiate u, u dashed is going to give 2x, and integrate v dashed to get v. Obviously the power, if it's an exponential to the power e, is going to stay locked. So that stays as e to the 3x, but however, because we have a constant in front of this x, that constant drops to the front and divides. So we're going to have 1/3 e to the 3x here. So that's our initial setup, and so we can now go forward and use the integration by parts method, which once again is here. So this is going to become the integral of, just u multiplied by v. That's going to be 1/3 x squared e to the 3x. We're going to subtract away the integral of u dashed v with respect to x. So u dashed v, 2 times 1/3 is 2/3 x e to the 3x dx. So this obviously is fine, but what we've got here is something that we need to use integration by parts with yet again. So if I just colour code this in, say, a lovely light blue, you can think about what to do with it over here. So let's think of a new u and a new v. If the letters confuse you, using them again, think of it as a w and an x. It doesn't really matter. but the u and v are arbitrary dummy variables. They can change depending on the integral in question. So for this one here, again have something algebraic and something exponential. So for this new one, I'm going to assign u as 2/3 of an x. I'll just colour this in so it's a similar colour to what we've got. That's not very similar. That's a bit closer. So I'm going to say u is going to be 2/3 of an x. Therefore u dashed, I can differentiate this. That'll just give me 2/3. And therefore that forces me to say v dashed must be e to the 3x. Therefore I can integrate that, and just like before where we saw what e to the 3x into h2, that'll just give me 1/3 e to the 3x again. So applying this a second time, the integration by parts technique, I'm going to have 1/3 x squared e to the 3x, then minus everything inside. So I'm going to put this in big daddy brackets, or big squared brackets, whatever you want to call them. Probably big squared brackets is more appropriate. We're going to have u multiplied by v, which is going to be 2/3 of an x multiplied by 1/3 e to the 3x. 2/3 times 1/3, that's going to be 2/9 x e to the 3x. Minus the integral of u dashed multiplied by v. So u dashed times v, 2/3 times 1/3, that's going to give 2/9. V, of course, rest of v is just e to the 3x. So then e to the 3x dx. So now I'm just taking care of the negatives. We're pretty much done. So we're going to have 1/3 x squared e to the 3x minus 2/9 single x e to the 3x. Then minus minus, this is going to become a positive. And if we integrate e to the 3x, of course that 3 is going to come down and end up being dividing by 3. So we're going to have minus minus plus 2/9 times 1/3, or 2/9 divided by 3. We're going to get 2/27. Positive 2/27 e to the 3x, all plus c. Question 5 is actually taken from an older exam question. So here we need to use integration by parts, or otherwise, but we're going to do integration by parts. I'll spoil the surprise now. We're going to integrate brackets x minus 1 brackets 5 minus x rooted dx. So first of all, then for part B, by the way, we're going to use that result to help us with part B. But first of all, for A, we need to set our u and v dashed. This isn't as obvious as before because both things are algebraic. This is algebraic, as is this. If you ever have a scenario like this where both are algebraic and both are trigonometric or whatever it might be, you pick the easier one that will differentiate down to 0 much easier. So the one that differentiates easier is the less complicated looking thing, which is just the x minus 1. We can hopefully see that, that will differentiate down to 0 quite quickly. If you differentiate it once, u dash should be 1, but if you differentiate again, it would vanish. Therefore, we set the other one v dashed to be 5 minus x. I'm going to write this as 5 minus x to the power of a half. In index form, it's easy to see what things will integrate or differentiate to. This one, we could use a u substitution to do it. Be my guest if you're not sure. I'm going to skip this step out now and just integrate by what I call inspection, essentially. If you're not sure where this is going or why I'm going to write this next, just revise your u substitutions or reverse chain rule. But essentially, because this is a minus x, we're going to get a minus at the front. The half, obviously, will go to power 3/2, because we increase the power by 1. And because we divide by the new power, we're going to divide by 3/2, which is the same as multiplying by 2/3. That minus is needed because it's a minus x. So if you used a u sub, and worked out du by dx, you'd get a minus term here. This is why it's going to integrate to negative 2/3 because of that minus x. And as I say, if that bit is slightly confusing, maybe just go back and revise for previous sub-chapters. So, based off this, we can now have a go at part A. So, this one here, this integral, is going to therefore be uv dashed minus the integral of u dashed v. In other words, this thing we have here. So, u multiplied by v will be x minus 1 multiplied by negative 2/3 of this. So I'm going to put the fraction first. So we have negative 2/3 x minus 1, then 5 minus x to the power 3/2. And then from that, what we're going to do is then take the do the negative integral, so minus off the integral of u dashed multiplied by v. U dash multiplied by v is just going to give us essentially 1 multiplied by negative 2/3, that becomes minus 2/3, 5 minus x to the power of 3/2. So carrying on and just neating it up, this first bit here we can leave as is, so we're going to get minus 2/3 x minus 1 and 5 minus x, close brackets, to the 3/2. Minus and a minus will make it a positive. So I'm going to take this 2/3 to the outside, and then integrate 5 minus x to the 3/2. Well, the new power will become 5/2. Then, of course, we divide by the new power. Dividing by 5/2 is the same as multiplying by 2/5. However, like I mentioned earlier with this integral, because it's a minus x, when we integrate, that will give us a negative term going back. So we get minus 2/5 here, which is an easy mistake to make or to forget. So finally, to just simplify this down again, we're going to get minus 2/3 brackets x minus 1 brackets 5 minus x all to the power 3/2. And then 2/3 multiplied by negative 2/5, that's going to give negative 4/15 of 5 minus x all to the power of 5/2. So that's part A. We can now use this to tackle part B, and in fact I've almost forgotten, of course. You tell me what I've forgotten. It'll be plus C, the constant of integration. Part B, though, because we have definite limits, we now don't need this constant of integration. We can now just apply this as it is. So therefore, for part B, the integral between 5 and 1 of x minus 1, and I'm going to rewrite this as 5 minus x to the half dx. That's going to be essentially just all of this integrated without the plus c constant of integration. So if I just cheat and just copy this bit here and plonk it here in a moment, like so, just like magic. I'll pause the video, then just copy and pasted. There's no magic here, sadly, apart from the maths itself. So that's going to be the integral in between 5 and 1. So hopefully you can see when I input the upper limit of 5 here, because this is 5 minus x, this bit will vanish to 0. Then minus 4/15, 5 minus 5, so I'm going to have 0 to something. So that again is going to give 0. So the upper limit of 5 is going to give us 0, when we minus off what we get when we input the lower limit 1. Well, this first term here, because there's an x minus 1, that again will vanish, so this whole thing will be 0. But the second thing, I'm going to have minus 4/15 multiplied by 5 minus 1, that's going to be 4 to the power 5/2. So minus and minus, of course, is a plus, so I'm going to have 4/15 multiplied by the square root of 4 to the power 5. Use a calculator if you wish. In fact, you probably almost definitely should. Then this simplifies to 128/15 in exact form. So hopefully you see, when we're integrating using integration by parts in between limits, we integrate as we would normally, indefinitely, and then we just apply the limits afterwards, not needing to worry about the constant of integration. So it is, of course, consistent with the other integration techniques we've seen. Question 6 I put in red. This one I don't think you'll find probably in the exams, but it's a beautiful type of result, which I just wanted to show you. What if we tried to integrate sine x e to the x with respect to x? Again, just remembering the integration by parts technique and result, we need to set what u is and what v is. So first of all here, using the LATE acronym, sine x is trigonometric, t, e to the x is exponential, which is e. T comes before e, therefore we're going to pick our u as sine x. Therefore v is going to be e to the x, sorry, v dashed. Because u is sine x, u dashed will be cosine x because sine differentiates to cosine, and v dashed, if that's e to the x, if we integrate e to the x, we get the same thing. So that gives e to the x again. So we can now apply the integration by parts technique, and we should see something quite interesting happen in a moment. So this is going to give us, if we integrate, u multiplied by v, so sine x times e to the x. I'm going to write it as e to the x sine x, like so. But I'm going to subtract away the integral of u dashed v, which is going to be cos x multiplied by e to the x. So I'm going to say e to the x cosine x dx. Now this here, we need to use integration by parts again. So over here, again we have something trigonometric cos and something exponential, the e to the x. So again, in this case, we'd set our u here to be cosine x. Now cosine would actually differentiate to negative sine x. So I put here minus sine x for u dashed. So if I set u to be cosine x, then of course v dashed must be the other one, which is e to the x. Then of course integrating e to the x, we get e to the x yet again. So applying these choices for u and v dashed to what we have here, we can then use the integration by parts technique again to evaluate this part of it. So now we're going to have, it's e to the x sine x minus, then now here our u v is going to be cos x times e to the x, so I'm going to minus ex cosine x off, then minus the integral of u dashed v, which is going to be minus sine x multiplied by e to the x. So it's going to be minus sine x e to the x dx. So if I just simplify this slightly by removing these big brackets, we've got e to the x sine x minus e to the x cosine x. Minus a minus, of course, is a plus, but because this plus here occurs after this minus, we still end up minusing a positive. And so actually what we're going to do here is it's still minus, in fact, sine x e to the x dx. But if we look now and notice, this is actually, this is actually the same as the integral we're trying to solve in the first place. Sine x e to the x dx is actually this. So what I'm going to suggest we do, we can call the integral we're trying to integrate, let's just call this I. So if I call this I for integral, then I can hopefully see that the integral itself is appearing here, because that's equal to I as well. So therefore, if I add the integral to both sides, if I just add I and treat capital I in its own right as a variable in an equation, I get that two lots of the integral is just e to the x sine x minus e to the x cosine x. So I'm going to factorize out the e to the x and write it as sine minus cosine. Therefore, dividing by 2, we get the result as required. So therefore I, which is the integral of sine x e to the x dx, just move this dividing by 2 out of the way so it's not in the way of my answer line. That's going to be just a half of all of this. So it's half of e to the x brackets sine x minus cosine x. So sometimes using integration by parts, the integral you're trying to find can repeat. And this is an example just very briefly showing you how to deal with it when that happens. We just get the integral on the same side of the equation, then divide through by how many lots of this integral are generated when we follow through and do the integration by parts technique. So now we've seen some examples, 6 in all, how we integrate by parts. It's now over to you to try some questions on your own. So if you turn to page 309 and 310 in the lovely blue book of yours, exercise 11F it is. Try all the questions and let me know if you're stuck. This integration by parts is a hugely important technique. It is one to absolutely master and not shirk. So keep going and don't give up in trying to understand how this works. Thanks for watching and listening. I hope to see you all soon, either in lesson or in the next video. So thank you very much and see you all soon.